this is the last part of the gas law chapter, the chapter dealing with gases. This is not technically a gas law, but it kind of dovetails in from the last chapter, which was all about stoichiometry, and this chapter deals with gases. So combine the two together, we got gas stoichiometry. And what is significant about this is it adds another layer of possibilities of prediction using a chemical equation that involves all gases, or at least some gases, within the reaction. Up to this point, the coefficients meant number of molecules and number of moles. Now we're going to add one more layer to that. So let's take a look at that. Okay, so we have here, let's take the equation that I had on the script. Propane gas being burned or combusted with 5 oxygens to get 3 carbon dioxides and 4 steams. Okay? Now, up to this point, we understand that what this is saying to us is that for every 1 molecule of propane we have, we need 5 molecules of oxygen to break it down completely into 3 molecules of carbon dioxide and 4 molecules of steam. That is one understanding of the coefficients, which we call the stoichiometry, the mathematical relationship with the coefficients. And also, and more importantly, for our ability to measure, has to be put into moles, in which it states that 1 mole of propane needs 5 moles of oxygen to break it down completely into 3 moles of carbon dioxide and 4 moles of water. So let's write that down. 1 mole of propane plus 5 moles of oxygen yields 3 moles of carbon dioxide plus 4 moles of steam. Now, I'm going to write that as a ratio like I did in the previous stoichiometry introduction. So 1 mole of propane for every 5 moles of oxygen, for every 3 moles of carbon dioxide, and 4 moles of steam. Because we're looking at the gas part of water, not the liquid part of water. Okay? Now, in a ratio, we can multiply everything by the same quantity and still keep the same ratio. Now, one thing I want to do here is to look at an example of how we can predict how we can change moles over to liters. And that is by using polymer. We talked about polymer. And in polymer, PV equals RT. And let's suppose that I have 1 mole of gas. Let's suppose that I have this at 1 atmosphere. And the temperature is standard. So it's 0 degrees Celsius, which is 273 K. And I want to know what is the volume of that. Okay? So I'm going to plug in all this stuff for PV equals nRT. Pressure is 1 atmosphere. Volumes are unknown. N is 1 mole. R is 0.0821 liter atmospheres over mole Kelvin. And temperature is 273 Kelvin. And to get, I'm sorry, that should not be an equal, that should be a time sign right there. And I'm going to get rid of the 1 atmosphere, so I'm going to divide by 1 atmosphere. Okay? And then when I divide all that out, my volume turns out to be 22.4 liters. And that is what we call a molar volume. That's the volume of 1 mole of a gas at STP. So I'm going to use that quantity, that 1 mole quantity. So I'm going to multiply 22.4 liters per mole by each of these 4 components. So this times this, times this, times this, and times this. Okay, and when I do that, I get 22.4 liters, because the moles cancel out, of propane for every 112 liters of oxygen for every 67.2 liters of carbon dioxide for every 89.6 liters of H2O. So now I've changed all my moles into liters by multiplying by the same quantity, which is 22.4 liters per mole, which is what happens at STP. And I'll come back to the meaning of that in just a little bit. Now that I've changed the liters, I'm going to get rid of these ugly numbers. So now at this point then, I'm just simply going to divide everything by the same number, only this time it's just plain the number 22.4. Now you're saying, why are you doing the same thing twice? I'm not. The first time I multiplied by 22.4 liters per mole, and now I'm dividing by 22.4. Those are not the same thing. It just allows me to be able to change the label so I can get what I want for the final product with the very important meaning that goes with this. So this gives me 1 liter of C3H8 for every 5 liters of oxygen, for every 3 liters of carbon dioxide, for every 4 liters of steam. And so I get the exact same numbers, only now I have a new meaning behind it, which is volumes of gas. So that means volumes of gas, moles, and molecules are what we can use the stoichiometry or the coefficients of those particles or substances in the reaction. Did it have to be 22.4 used for that? No, it doesn't make any difference what the conditions are. And that's, I picked one just as an example, but I didn't have to. I could have picked anything I wanted, and I'm still going to get the same ratio back. And when I say liters, it isn't just liters either. You could have cubic meters, you could have cc's, you could have quarts, gallons, pints, whatever. The ratio has to be the same for all 4 numbers, has to have the same label, but the relationship is identical no matter what label you use, but they got to be the same all the way across. Okay? So STP is important for this because the conditions remain constant to allow those numbers to change, so I could have picked anything I wanted for that. I just happened to pick a convenient one I happen to know. Okay? So volumes of gas, moles, molecules are what that refers to. Okay? Now, so let's go to the first example in that lesson, the script that I have there. If I have 12.8 liters of propane, I want to know how many liters of carbon dioxide would be produced. Again, it doesn't make any difference what the conditions are, since the conditions are the same for the entire reaction. So this becomes a simple one-step conversion problem. And no, not all the problems will be this easy, sorry. If I put a time sign, fraction line, And I'm going to put liters of C3H8 on the bottom and liters of CO2. And I'm using that same equation. Okay, equation, again, I'll put this over here for this. We have C3H8 gas plus 5O2 gas yields 3CO2 gas plus 4H2O liquid. And when I go from liters to liters, it's like going from moles to moles. All I use are the coefficients of the chemical equation describing this system. So we have here liters of CO2. The number in front of the CO2 is 3. Liters of C3H8, the number or the coefficient in front of that is 1. So I'm simply going to multiply this by 3. 38.4 liters of carbon dioxide is what I'm going to get.